Alright. So, now what we will do is we will look at how to we actually, we have looked at the shape functions. The next thing we have to see is the start with the wave equation, go to the weak form. That is the strategy of FEM. Right. So, what is the let us see what is the equation that we can use. Maxwell's equations, everything starts from Maxwell's equation, right. So, the first equation is del cross H is equal to j omega epsilon E, first equation. Second equation is del cross E is equal to minus j omega mu H, alright. So, what we will do is like in the previous case, we can consider one polarization, the other polarization the same kind of logic will follow, right. So, we were doing TM polarization in surface integral. So, H in the plane and Ez. So, if I want to continue to talk about 2D TM polarization, okay, that is what I want to continue to talk about for definiteness. So, what do I need to talk about? H in the plane, that is what I will solve for, because that is the thing I can express as a vector, right. E is a scalar, there is no point of vector over there. Okay. So, what I will do is now, yeah, Hx, Hy and Ez. So, let us take this equation for example, right. So, del cross H, we have done this before. In order to use the other curl equation, I needed to remove something from the right hand side of the first equation, and that was a epsilon r, right. This epsilon over here was epsilon r epsilon naught, and epsilon r is a function of space. So, I can bring this over here, epsilon r is a function of space. This is going to be equal to j omega epsilon naught E. Next step. So, I am ignoring the j term for now, okay, but it is easy to add it in. Next step would be to take curl on both sides. So, what happens is, where I replace this and I am going to get j into minus j. So, omega squared epsilon naught mu r as a function of r and a h, right. So, I have eliminated the electric field and I have got one vector wave equation in my unknown, which is h, right. So, I can just combine this into one equation. I can just write this as del cross 1 by epsilon r so this will become a k naught squared mu r right. This is my vector wave equation. So, typically what is given to me in this problem is epsilon r mu r as a function of space is given to me, maybe some incident field is given to me, object is given, find out the fields everywhere. Okay. So, this is the vector wave equation. Okay. Now, given some kind of a domain over here with some object over here, right, this is my epsilon r mu r. Okay. So, what do we have to do in the FEM? We will be breaking this whole thing into little triangles, right, all over, and then doing. So, if I call this expression over here, let us call it say f h, this whole expression. So, the wave equation is f h equal to 0, right. So, that is also what was the term we had used in 1D, the residual. When I took everything onto one side, I called it the residual, right. So, ideal world, I want f h r is equal to 0 for every r, that is the solution to the wave equation. Okay. Not possible. So, what is the next best thing I settle for? In an average weighted sense, right. So, instead FEM says weighted residual method, integrate over domain. So, take some mth testing function. Now, I must take a dot product because this fh is actually a vector, right. Right. So, this is the starting point for the FEM, weighted residual method. By the way, any differential equation, this is the approach you will do. Form the residual, enforce it in an average weighted sense. Okay. So, subsequently we will see what we need to do to convert it into the weak form. Okay. This is fine. Okay. So, we will continue with our discussion of 2D vector FEM, and what we have so far is the wave equation, right. Wave equation. One thing I wanted to mention that when I took this equation over here, there's also actually a j term over here, which I have ignored for now. Depending on the problem, you will need to add it in. Okay. So, in this discussion, we are assuming there is no current supplied. If there were a current, then it would also appear in this FH equation. Okay. So, so the residual will also include this j term, just to keep in mind that in general it should be there. Regardless, the philosophy of FEM is the same, weighted residual method. I take my testing functions and impose this residual to be 0 in an average sense. Okay. So, now let us open this up and see what the weak form is obtained from here. Before we do that, we should have an idea of what we are going to do. So, what was the key trick in 1D that allowed us to convert this to weak form? Integration by parts, and we needed that because there is a double derivative, right. You can see fh over here, there is a del and there is another del over here, del cross del, there is sort of a double derivative term over here, and we do not want to deal with double derivatives given a chance. So, we would like to convert it into single derivatives, right. So, integration by parts is what we will have to do, but in 2 dimensions. So, that is something, if I tell you integration by parts in 2 dimensions, I do not think it rings a bell immediately. So, we will see there is a very simple expression from vector calculus that will help us there. Okay. So, let us write this out. I will just write this on the top over here, Tm remember epsilon r is a function of space, okay, otherwise the problem is not interesting. Okay. So, I have written dot dr, since we are considering a 2D problem, this is a 2-dimensional differential. For example, this could be a dx dy z hat. Okay. So, I am writing it in short notation as d vector r. Okay. So, now is the part where we will have to apply integration by parts. So, let us look at a very simple identity. This first part of the left hand side, okay, this is what we are going to look at. The second part is easy. So, what does this look like? This looks like A dot del cross, can I write it as simply this, right. A is Tm, B is 1 by epsilon curl of H. Okay. So, there is a simple way to rewrite this. Okay. These are standard identities in vector calculus. Okay. Next, what do? We will substitute this identity inside the first term of the integral. So, what happens we will just take the first term. what happens of the first term? So, let us write out the first term. So, dot product commutes. So, A dot B is B dot A, right. So, the first term will become, let us use this guy, the first term here. So, del cross A, what is del cross A? Tm, right. So, the first term will become, so there is an integral over here, del cross Tm dot del cross B, right. Now, B is, sorry, there is no del cross B, just B, right. So, that is 1 by epsilon r del cross H, okay. Then is del dot Tm cross 1 by epsilon del cross H. Okay, the whole thing is that fine, nothing very surprising over here. So, have I escaped the second derivative? Is there any second derivative in the first term? Negative. Second term? It is there. So, what do we do? But if I integrate, I mean, how do I integrate? Does it look like some theorem of vector calculus you have already seen? Del dot something and a surface integral over it. So, that is like which theorem? 2D divergence theorem, exactly. So, 2D divergence theorem, right. So, this term will remain as it is minus. So, the second the double integral will become a what integral? Line integral, right. The divergence theorem helps us to reduce one dimension. So, outgoing flux becomes a line or surface depending on what. So, if in 3D a volume integral divergence over entire volume becomes a flux integral over the surface. In 2D a surface integral will become a line integral and how much flux is going out of the line. Okay. So, del dot something is replaced by this whole expression. So, Tm cross 1 by epsilon r curl of H dot n hat dl. Okay. So, what is my, this is, if this is my computational domain, omega is the whole interior thing and gamma is the surface or the line in this case. So, have I now escaped the double derivative? Gone, right. The first term does not have it. The second term, by using the 2D divergence theorem, that is also gone, right. So, for those of you who are having trouble recalling this 2D divergence theorem, I will just write it over here. So, double integral of del dot f, right, that is what we are talking about, integrated over a surface, that should be equal to f dot n cap dl over c. So, I mean, it looks slightly complicated with all this del cross and all, but it is not very difficult. So, putting it all together, what does my weak form look like? First term will remain as is, right. So, first term will become curl of Tm dot 1 by epsilon r curl of H, that is my first term. Then I have this guy, the second term, k naught squared mu r Tm dot H. These are the two terms which are still double integrals. So, that is dr, right. Okay. In fact, this dot need not be here, right? It's just the dot product is over here. There's no, this dr for example could be just dx dy. Yeah, the small part of the area of the triangle basically. Okay, so I can get rid of this. Yeah, so it's all consistent. So these are the first two terms, and what am I left with? I can take this guy onto the right hand side. So this is the 2D weak form question. No, gamma can be. Okay, good question. So should gamma be the overall boundary of this medium or the boundary of the triangle? Overall boundary of this medium, because if you look at this entire slide, have I made any use of a triangle anywhere? No, I mean I have just indicated by figure, but the triangle does not appear because I have kept h as h, whatever h may be. Later I will write h in terms of triangles, okay. But as this goes, this divergence theorem talks about the overall boundary. So that is why this boundary term is coming just on the boundary. Now, and this does not in any way force me to have h to be, you know, subdomain basis functions or entire domain basis functions. H is h, whatever it is. So very general. We don't have the tessellation yet, right? We just used basic identities from vector calculus. We don't have h, the tessellation so far. Whole domain, everything. So it makes sense to do all of the vector calculus simplifications first and then go to tessellation, basis functions and so on, because I mean that way you reduce the complexity of your problem. Okay, so n hat will be the outward norm. I have just drawn a rectangle, it can be any shape you want depending on the problem. Fine. So let me ask you, supposing instead of such a computational domain, I had a bit of a slightly different domain. So I had the outermost triangle like this, and I had some missing metallic, you know, some part where I know, let's say a metal piece. I know the field inside the metal is 0. There is no point in simulating and finding it out to be 0, right? So supposing I want to exclude this hashed region from here, what would change in what I have done? Right, so this divergence theorem will get modified to have two line integrals, so that you are integrating only over this green region, right. So if I call this gamma and I call this gamma dash, in that case the RHS will become an integral over gamma minus an integral over gamma dash, and the expression remains the same, okay. And the region gamma here will exclude this hash region, right. So this is something that we should keep in mind for you know, regions where you don't want to do any simulation, where there is no use, right, because I mean the larger your computational domain, the more price you will have to pay in terms of computation, okay. So this is a weak form, this is fine, okay. So now we come to the very crucial part, which is boundary condition, right. So you can see that carrying the trick forward from 1D, the boundary condition is going to appear this right hand side term over here. That is where I will get to impose the boundary condition over here. In the 1D case, what was my right hand side term like? It was a du by dx. In the case of 2D, it is not exactly du by dx, but it is curl of h. Curl of h has appeared over here, and now I have to figure out how do I approximate this. Again, without doing the math, what do you expect will happen? In the 1D case, I saw du by dx, I replaced it by some constant times u, because that best simulated how a plane wave behaves. Those constant depended on the medium and all of that. So do you think, I mean the physics will not dramatically change when I go from 1D to 2D. So what do you intuitively expect to happen? I should get some constants and h, That's the form I should expect. Pardon me? Yeah, I mean, but linear in H, it's not some derivative in H, right? There will be some linear expression in H is what I expect, okay? So, it's good to do this check before you do the derivation so that, you know, your intuition matches your math.